Welcome to this video. In this one we're going to look at Z-scores. So Z-scores are incredibly important, and because they tend to come in at the end of probability, and then we see them quite a lot during statistics, and in particular the inferential statistics. That is all going to be based on Z-scores. So they're a hugely important part of the course that, I would say it's so important that you understand them and that you can work with them. So this video will probably just be that little bit longer, just to warn you, but just to break it down, what we're going to do if you want to jump to a part in particular, if there's bits that you're not sure about. So if you have the basics and want to skip on, that's absolutely fine. So what we're going to do is first I'm just going to revisit the empirical rule. Then I'm going to look at what is a Z-score, and I'm going to do those two together. I'm going to use the empirical rule to really discuss what a Z-score is. Then we're going to find probability using Z-scores. So that's going to be a really straightforward way. And then we're going to use the standardizing formula, which will then lead to using Z-scores again. So each bit will be linking up to the next, and finally we're going to look at problems. So I have an exam question here that we can see. So basically in statistics we tend to see a lot more wordy types of problems. So what I want to do is just go through one of those, because often I find students struggle with converting the words into what we're used to, so like the mathematical statement, and often when you get to the mathematical statement they can do it from there. So if we can work on that, it might help some of you. So here's our empirical rule here. So just as revision, the empirical rule, there's three different places that you need to know. So you have to know that about 68% of the of the observations are between plus and minus 1 standard deviation. So I'm just going to try shade this in for you then so you can see. So we're talking about this piece here. So we have what's called a normal curve. A normal curve is one where the mean, the mode, and the median are all at the same point. In this particular question, we are only shown the mean, which is here, and which is used for mu. So we should know that given a standard normal curve, that 68% of the observations lie between plus and minus 1 standard deviation. So the normal curve is symmetrical, which is hugely important. So this piece, I'm going to try to go over it. So this piece here on the left, so this standard deviation here is the same as this standard deviation here. Okay, so then we have 95% of the populations are between plus and minus 2 standard deviations. So the observations lie all the way out to here. So we have something out to here. Okay, so for that one we have about 95% lie in there. And lastly, there is 99.7, so practically all of the observations lie with, well, basically out to 3 standard deviations. Okay, so when we look at the normal curve, it's broken into 6 pieces. We have 3 on the left and 3 on the right, and that center point is our mean. Okay, so if I move to the right, I'm talking it's the mean plus standard deviation. If I move to the left, I'm talking that it's mean minus a standard deviation. So the mean is that middle point. So moving to the right, I'm going to add a standard deviation. Moving to the left, I'm taking one away. And we would have the same for 2. So you can see how it's split up there. Now, the number of standard deviations, that can be represented by the letter Z. Okay, so in our first example here, this 1 is basically Z is equal to 1. So there's 68% of the observations lie within plus or minus 1 standard deviation, but that 1 is Z. In the second example, 2. So they're plus and minus 2 standard deviations. And in the third example, it's 3. Okay, so they are all our Z. So Z represents the number of standard deviations from the mean that something lies. So we're constantly thinking about Z as the number which represents the number of standard deviations from the mean. And keep that in mind when you're doing it, because if you can understand that, it will make the questions a lot easier. So that hopefully has answered what a standard deviation, or sorry, what a Z-score is. So let's take a look at our first problem. So I wanted to do an example finding the probability using Z-scores, and I'm going to be doing 3 different ones here because there's really 3 different things that we need to be able to do when it comes to Z-scores. Now on the right hand side I have a little picture of page 36 and 37 of your log table. So if you have your log tables with you, do open that page because it's important that you get used to it and you can use it. Now, the only thing that's missing from I've kind of cut away some of it. The thing that's missing that is actually, I think, one of the most important bits is at the very top of this page, so page 36 in your log tables, you'll see that it says this, Z is less than or equal to Z. Okay, and this is hugely important, and I would say use this as a guide, because what that basically is telling us is there has to be a less than or equal to sign. So you see this sign here, that has to be less than or equal to if we want to use the tables. So if it's not less than or equal to, we cannot use the tables as they are, and we're going to see that over the next 2 examples. Now, in this example here, it's basically find the probability where Z is less than or equal to 1.35. So I have a blank normal curve up here. So let's take a look at what that means. So 1.35, so we're roughly about here. I want to find the probability where Z is less than that number. So less than means to the left. So basically I'm talking about this portion here. Okay, so what is the probability that Z is less than 1.35? So as you can see, my diagram here that I've shaded in looks very like this one here. Okay, on the right hand side, it's shaded from the Z-score to the left, and in my probability where it said Z is less than or equal to, I have the same symbol, so I've got less than or equal to. So what I'm going to do then is, because everything looks like it should, I'm going to go straight to the tables. So I'm going to look up 1.35. Now you might notice I have 1.3 here, but to get that extra 5, I have to look across the top. So this is 0.05. So what we do with these extra bit along the top is we basically add it on. So I have 1.3 and I'm adding in 0.05, which is 1.35, which is what I'm looking for. So if I highlight this, so that is my answer here. Okay, so my answer then is the probability. That's, sorry, let me change back to the blue so you can see it. So the probability that Z is less than or equal to 1.35 is equal to 0.9115. And just for yourself, what that means is that's 91.15%. So I know that 91.15% of observations lie below 1.35 standard deviations above the mean. So this time we're only talking above the mean because that Z is positive. Okay, so let's take a look at our next example. So example 2, it is finding the probability using the Z-score. So the same question. So let's take a look. I'm first going to draw it on my normal curve. Now you might notice straight away that there's something different, and that is that this number is now negative. So I'm actually working to the left of the mean. So I'm dealing with this section here. So I want to figure out what's the probability of this happening. Now if you see, I'm just going to have to put this back because it got taken away the last time. So remember, at the top of the tables it said Z is less than or equal to Z. Okay, so I'm looking out for this less than sign, and look, here's my less than sign, so that's all good. So I can go straight to my tables and look it up. But problem, I go to my tables and actually the tables don't have negative numbers. They only have the positive numbers. So see, they only start at 0.0, that's my smallest, and they go all the way up to 3.09. So what that means for us is we have to figure out another way of dealing with that negative. Now, I did mention earlier that the normal distribution is symmetrical. So the green piece that I have drawn should technically be the same as if I drew this green piece up here. Okay, so that should hopefully be the same. Now, what that means for us is it's the probability that Z is greater than or equal to 1.35. Because if this piece here is minus 1.35, its symmetrical point on the other side is 1.35. And we're talking about to the right, so we're talking greater than. Okay. Now, problem with that is I now have a greater than sign and I want a less than sign. So that's not correct. So we have to use a really important property of the normal distribution, and that is all of the area underneath this curve, or the full probability of this curve, is 1. So what I'm going to have to do here is say, well, I can't work out the piece that's going to the right of 135, but I'm actually going to work out all this instead. So I'm going to work out this piece here, which I can do because that yellow piece there is the probability, and I'll just write this in. So the yellow piece here is the probability that Z is less than or equal to 1.35. Okay, so I know that if I have 1, which is all of the probability, and I take away the probability that Z is less than or equal to 1.35, I will get the little green piece. I'll just re-highlight that so we can see it. I'll be able to work out this piece here. And when I work out that piece there, it'll be same as this little piece here. Okay, so can I work with that now? Well, just double checking. So just to double check, yeah, here we have a less than or equal to symbol. So I can work that out. That's absolutely fine. I'm going to go to the log tables, page 36, page 37, and again look up 1.35. So I'm left here with 9115. So I have 1 minus the probability that Z is less than or equal to 1.35 is 0.9115. So that gives me 0.0885, which means that is 8.85%. So 8.85% lies in this section here, where Z is less than minus 1.35. So example 3 is now where we're trying to find the probability between two values. So let's put in our two values. So this one here is minus 1.35, and we have one here that is 1.35. So I am trying to find this piece here, so the bit that I've kind of shaded in here, I'm trying to find the area of that. Now, again, that's not what the tables allow us to do. Remember, the tables only allow us, and if we look up here, they allow us to just go all the way back. And remembering the probability that Z is less than or equal to Z, that appears at the top of the tables on page 36. So what we can do in this case is I'm going to basically work out this yellow piece here. Okay, so I'm going to work out the yellow piece, and when I do that, I'm going to take away this red piece here, okay, and then I should be left with the bit that I actually want in the middle. So what that means is I'm going to basically do the probability that Z is less than or equal to 1.35, so that's the yellow piece. And then I'm going to take away the probability that Z is less than or equal to minus 1.35. Now, if you remember, we did say that we can't do a negative. So the probability that Z is less than or equal to 1.35, that's absolutely fine. That piece I can do, look up in my log tables. But this, as we saw in the last example, became 1 minus the probability that Z is less than or equal to 1.35. Now, do go back and look where I got that. I've skipped a few steps here just to move along because it is worked fully in the last question. So let's go to our tables and find that figure. So 1.35, which is 9115. So we have 0.9115 minus 1 minus 0.9115, which is 0.9115 minus 0.0885, and that gives us 0.823, which is equal to 82.3%. So we could say 82.3% of the data lies within plus and minus 1.35 standard deviations of the mean. Now, so we're going to move on now to looking at the standardizing formula. So the standardizing formula appears on page 34 of your log tables. I would say do get familiar with your log tables for statistics, because your log tables have page 33, 34, 35, and then the Z-scores on 36 and 37. So you have 3 full pages of formula, and you don't need them all. So it's important that you're able to identify the ones that you need. So the standardizing formula, which we have just up here on the right hand side, just for ease, is here. That appears halfway down, and it is called the standardizing formula, but you do need to know this. Now, this is used to find a Z-score. So in the previous 3 examples, we've been given our Z-scores. Now we're going to look at an example where they haven't given us the Z-score. They've just given us a number that we then have to standardize, or to put into basically how many standard deviations that number means. So remember, every normal curve is broken into plus 3 standard deviations and minus 3 standard deviations. So a number, like in this particular example, so 68, well, what does that mean? Well, to understand what that actually means, we first have to turn it into a Z-score. Now, a formula for standardizing or finding the Z is x minus mu over standard deviation, where mu, if you want to make a note, hopefully you know this at this point, but this is the mean and this is your standard deviation. Okay, so let's find that. So Z is equal to x, in this case is 68, so that's given here. I'll just try and mark them as I use them. And then there's going to be mu, which is 60, and standard deviation, which is 5. Okay, so let's go from here. Minus 60 over 5. So that gives us 8 over 5, which is equal to, so that's 1.6. So when you've worked out your Z-score for this question, we then go back to what they initially gave us, which was this, and we standardize that, or we basically put in our Z-score. So instead of x, we put in Z. We follow whatever inequality they've used. So you have to follow. If they had started off with less than or equal to, then we have to have less than or equal to now. If they had given you greater than or equal to, you have to use greater than or equal to. So we're basically trying to find the probability when Z is less than or equal to 1.6. Remember that we can only deal with things that are less than. This is less than, so that's absolutely fine. So let's go look for our formula, which is just 1.6. And here is our answer here. So that is equal to 0.9452, which is equal to 94.52 So what that's telling us is the probability that a random variable x being less than 68 is 94.52, given that it's coming from this data that has a mean of 60 and a standard deviation of 5. So be very familiar with this. I'm going to do one more example of the standardizing formula just so we kind of get into the swing of it. Apologies, I probably should have drawn on this first to show you. Here's our 1.6 and this is what we're looking for. Since it was a straightforward greater than sign, or sorry, since it was a straightforward less than sign, I suppose I didn't really do that, but it is a good idea to do because you can then see, does my graph look like what it looks like in the log tables, or do I have to do some changes to it? So example 5 then is a similar question. It's actually a follow-on, and they want us now to use to find the probability where this random variable x is between two numbers, so 52 and 68. So it is a follow-on from the last question, so the mean hasn't changed, the standard deviation hasn't changed, and one of our x's is still 68. So from that point of view, I know that my z for that is 1.6. So we can just make a note of this. It's just the way I've taken the example, but these were given one after the other. So now we have to find the z-score given the x is 52. So let's go do that. So z is equal to 52 minus 60 over 5, which gives me minus 8 over 5, which gives me minus 1.6. Now that is so hugely important. Please don't lose that sign. So now I think it will be beneficial to see this here. So this is minus 1.6 and this is 1.6. Okay, so we're trying to find the probability that it appears somewhere within here. Okay, so first thing we're going to do then is we're going to put it back in the form that we needed for the tables, and that's using z's. Instead of 52, we're going to replace that with 1.6. We're going to keep the signs or the inequalities the way they are. X now becomes z because we've standardized it, and it's going to go to 1.6. Now, if you remember how we do this, we have to work out the probability that z is less than or equal to 1.6, which brings us all the way to the end, and then we have to take away this end piece, so z is less than or equal to minus 1.6. But remember, we can't do a negative, so we're going to have to change that. 1.6 minus 1 minus the probability that z is less than or equal to 1.6. And let's go to our log table. So they're both the same number, which is nice. So we can just go straight to 1.6, which is here. And let's work this out. So this is equal to 0.9452 minus 1 minus 0.9452. Now I'm just running out of space, so I'm just going to put my answer. So it should work out 0.8904 as you work through it, which is 89.04%. So hopefully now you're beginning to see as we move on, we're still using the basics that we learned on Z-scores in the first few examples. So it is really, really important that you're able to get those basics and you understand those basics. Make sure that you're able to read from the table. Make sure that you're able to work with a negative Z-score. So how do we work with that? Make sure you are able to work with when it says greater than. Make sure you're able to work with a compound error where we have two inequalities, where it's within two values or between two values. They'll all be really important. Now, the sixth example that I'm going to do is actually an exam question. I actually don't have it to hand which exam question it is, but data on earnings were published for a particular country. The data show that the annual income for people in full-time employment was normally distributed with a mean of 39,400 and a standard deviation of 12,920. So they've given us two bits here. So government intends to impose new taxes to incomes over 60,000. Okay. Find the percentage of full-time workers who will be liable for this tax correct to one decimal place. So they want us to find, well, the probability or the percentage, if it's the same thing, that income, which is a random variable, x, is over 60,000. So this is what we start with. So we have to be able to create this mathematical statement that the probability of x, that x is greater than 60,000. That's what we're looking for. Now, when we do write this, then we can kind of look and see, oh, okay, well, I have an x, but I want to be able to use my z-scores, so I'm going to have to use my standardizing formula, which is z is equal to x minus mu over sigma, which is standard deviation, which is 60,000 minus our mean, which is 39,400, all over 12,920. Now, we'll get an answer here, but remember our log tables only actually go to 2 decimal places, so we have to keep the same. So we get 1.944, but I have to round that to 2 decimal places, which is 1.59. So going back to my initial statement, I now can replace that with z is greater than 1.59. So now what I'm going to do is I'm going to go to my log tables, and you should see that this is now a greater than sign, and so I cannot use my z-scores as is. I have to be able to have a less than or equal to sign. So remember how we dealt with that? Instead we said we know the probability of all of it is 1, and then we take away the probability that z less than or equal to 1.59. Okay, 1 minus 0.9441, and that will leave me with 0.0559, which is equal to 5.59%, and they said 1 decimal place, which will be 5.6%. Okay, so that is an example of how we would use our z-scores to answer a more problem-solving question. So on to part 2 of this question. So in this part, we're going to see how maybe we sometimes have to work backwards to find our z value given the probability. Okay, so in this case, they've said the government will also provide a subsidy to the lowest 10% of income earners. Find the level of income at which the government will stop paying the subsidy, correct the nearest euro. Now, so the lowest 10%. So my advice on this is to just really quickly just sketch out a normal distribution. Now, mine's not fantastic, but it'll just give us a sense. So we have our center point there, which is mu. So the lowest 10% then is going to have to be somewhere down here. Okay, it's the smallest 10%, because remember, it is symmetrical. So we have half of it this end, so there's half above mu and there's half below mu, so 10% would have to sit there. So that's some value. So let's call that value minus k. Now the reason it's a negative is because where it sits. Remember, our z values to the right of mu are always positive, and the z values to the left of mu are always negative. So what we're trying to find is the probability that z is less than or equal to minus k, and that's because it's the lowest 10%. So what we're finding is to the left of this value minus k, but they have told us that that's 10%, which is 0.1. Okay, so straight away we can't go to the tables with that because it's 0.1, and remember our tables only give us the smallest probability that the tables give us, I'm talking about the tables on page 36, is 0.5. Okay, so we can't use that. So how we work with it is we want to get rid of the negative, which if you remember it's 1 minus the probability that z is less than or equal to k. So remember, instead of getting the lowest 10%, we then look at the top 10%. So I'll put this in here. So we try to find this is the probability that Z is greater than or equal to K, but we can't do that either because it's not possible to find greater than in the tables. Remember, it's only less than. So then we have to work on and say, well, instead of that, I will do 1 minus the probability that Z is less than or equal to K. And that comes from the fact that the area underneath that whole curve should add up to 1. Okay, so this should then give me 0.1 here. I'm going to rearrange, so I'll get the probability that Z is less than or equal to K, and that gives me 0.9. I can look that up in the tables. Now, that value doesn't appear exactly in the tables, but if you go to your tables and look up 1.28 and 1.29, you'll see that, you'll hopefully see that 0.9 sits somewhere in between those two values. So 1.28 is 0.8997. 1.29 is 0.9015. So it's actually closer to 1.28. So we would say that K is equal to 1.28. Okay. Now, when we have that value, just remember that the Z is actually a negative. So Z is equal to minus 1.28. Now, the question actually asked us to find the level of income. So that actually gave us, so just from the previous part of the question, they had told us that the mean is equal to 39,400. They had told us that sigma standard deviation is 12,920, and we wanted to find x, which was the level of income. Okay, so level of income. So how we do that is we use our standardizing formula, which is Z is equal to x minus mu over the standard deviation, and that appears on page 34 of your tables. So let's sub in what we know. So we actually do know Z. Now this is where it's so important that that's a negative, because if you put that in as a positive Z, you're going to get a different answer. You're going to find basically the lowest 90%, which is not what we want. So x then we don't know, so we can leave that as x minus 39,400 all over 12,920. So that will multiply both sides by 12,920, which will give me minus 16,537.60 equals x minus 39,400. And we'll rework that and find that x is equal to 22,862.40. Okay, but just beware the question, it asked us to round it to the nearest euro. So, you will lose some marks if you do not do what the question asks. So do keep an eye out for things about in what form they want your answer, or how they want you to round it, whether it's nearest euro, whether it's so many decimal places, significant figures, anything like that. So this rounds down to 22,862. So that is kind of the cutoff for where it will stop paying subsidies. So don't panic if you're given a question that's, I suppose, slightly different to what we know. My biggest advice would be make sure you're happy with when you're looking up the Z part in the table and when you're looking up the probability in the table. So if the number is in the bracket, so here, if we know that number, we're looking up the Z-score because that is Z. While if we're looking up this number, okay, that is the probability is that number, and we have to be able, we look in the tables and out to get our Z, so in the bulk of the table, and we're working outwards to find Z.